Hey everybody, it's Wednesday, October 21st. As you can see here on the AIM today, we are going to be spending this video talking about how we can apply concepts of projectile motion to solve problems for projectiles fired at an angle. So for today, our main focus is really just to try to take everything that we talked about yesterday, use it to solve a full-on calculation problem, and then we're going to go ahead and take a look at a bunch of conceptual examples. So to start us off, the first thing we're going to do is solve a calculation problem. This one is one that was just made up, and so I'd like you to write the chart in your notebook and then get going on solving it. It has 3 parts. This problem says a ball is launched with an initial velocity of 4.47 meters per second at an angle of 66.0 degrees above the horizontal. Part A is what was the maximum height the ball attained. Part B asks you how long did the ball take to return to its launching height. And C, what was its range. Now, before I have you go ahead and solve this one, I want you to do this one entirely on your own. The main point of this problem here is asking you to solve for all these things, obviously, but I want to focus you in on this part particularly. Because yesterday I mentioned something to the effect of, we're going to assume that these objects are basically launching out of the ground. And so the second they're released, they're at ground level, and then they're coming back down to the ground. And of course, that's a little bit of an insane oversimplification of a problem. And so effectively what we're going to do in a lot of these problems is we're going to assume a person throws the ball from some height above the ground. And then we're really just going to go and consider what happens while it's in the air until it gets back to the height from which it's launched. Maybe part D of the question after that will say, if the person released the ball a meter above the ground, how fast was it going when it hit the ground? But you won't see that until we get to some of the later homework problems. All right, so based on what we said yesterday, you should be able to solve this whole thing. So I'd like you to take, let's call it 7-8 minutes to pause this video here, solve this problem. You want to make your chart. You want to solve for everything that needs to be solved for in parts A, B, and C. And when you hit play, we'll go over the whole thing. Okay, so your first move for all of these projectile motion problems is to make your chart. And for this problem, your chart should look like this. Now, of course, in addition to writing the basic variables in the chart, first, I also showed the work for the initial velocity components, because you definitely need to be able to do that first. So before I wrote down those components, I wrote in the chart VFY equals 0 meters per second. I wrote AY is negative 9.8 meters per second squared. I wrote AX is 0 meters per second squared, and I wrote X naught and Y naught are both 0. Once you do that, you have no other choice but to go and solve for your initial vertical and horizontal velocity components. So the first one I did for no reason at all was V naught X, and I solved for V naught X using the equation V naught times cosine theta. So you plug in your V naught, which they told us in the problem was 4.47 meters per second, and I multiply that by the cosine of my angle, which is 66 degrees. And when you do that math, making sure your calculator is in degree mode, you get 1.818 meters per second, or to 3 significant figures, 1.82 meters per second. Moving on then, I calculated V naught Y, and V naught Y is V naught sine theta. So I took my initial velocity, 4.47 meters per second, multiplied it by the sine of the angle here, which was 66.0 degrees. And when you do that math, you get an initial vertical velocity, V naught Y, of 4.084 meters per second, which is very obviously not equal to 4.09, right? That's 4.08 meters per second here. And so let's just fix that real quick. And so because our initial vertical velocity is 4.08 meters per second, we'll put that here, and now all is right with the world. So it's important to recognize one thing here very quickly, which is that because the angle is so huge here, 66 degrees, we definitely should expect to see a vertical velocity component, v naught y, which is considerably bigger than the v naught x. Now, I understand this like scale model triangle diagram here is a little bit of a sketchy way to go about thinking about that, but it works. When the angle is larger, we should expect to see a larger initial velocity in the y direction than we would expect to see in the horizontal direction. And so because I have those values now, I went here and filled them into the chart. I have 4.08 meters per second for my v naught y, and I have 1.82 for v naught x and vfx. Okay, so now that we have all the right variables here, we're ready to go ahead and solve the problem. And part A of this question asked you, what was the maximum height the ball attained? Now, because this question was part A, I decided to just go about answering this question without doing anything else first. And of course, now the point that we're trying to make here is pretty straightforward, I think, because we have the initial vertical velocity, the final velocity in the vertical direction, the vertical acceleration, and we're looking for the max height. And so the equation that we're going to use for delta y is the time-independent equation. The time-independent equation is your go-to equation for maximum height because you don't need the time to be able to solve for the maximum height. Really, all you need to know on the surface of the Earth then is the initial vertical velocity. Because if you know the initial vertical velocity, then you just plug that in. You always know what the acceleration due to gravity is going to be, and then you solve for your maximum height. So we get delta y equals negative v naught y squared over 2 times ay. And so that gives us negative 4.08 meters per second, whole thing squared, over 2 times negative 9.8. Notice the negative signs are going to cancel, giving us a positive maximum height, which we should expect to see. And that maximum height is 0.849 meters. And so now that we know that maximum height of 8.49 meters, we can go ahead and add that to our chart. And so now, notice, we've almost got every single thing filled in on the right-hand side of the chart, on the y side of the chart. Part B asked us, now let's just go back to the question here very quickly. Part B asked us, how long did the ball take to return to its launching height? So we can go ahead and solve for that. There's a number of ways that you can answer that question. I decided to show it like this. We have the total time here as our unknown, and I decided to do it what I'll call the shortcut way, by using the fact that the final velocity when it gets back to the launching height is just the negative of the initial velocity, which was 4.08 meters per second. So to find the time here, I'm going to just use my final velocity equation, vfy equals v naught y plus ay times t. So I solved this for t by writing vfy minus v naught y over ay. When I do that and plug in those numbers, I get negative 4.08 meters per second minus 4.08 meters per second over negative 9.8 meters per second squared. And when you do that math, you get 0.833 seconds to 3 significant figures. Now, of course, this is not the only way that you could have solved this problem. You also could have done it what I would actually consider to be the longer way, which would be to find the time to the maximum height and then double it. And so just in case anybody showed it here, the longer method is to use the same equation, vfy equals v naught y plus 2ad, and then, sorry, I just said that wrong. vfy equals v naught y plus at. Recognize here that the final velocity is 0 at the maximum height, and so that just gives you time is negative v naught y over ay. when you plug in your numbers here, 4.08, and of course that's got to be negative because we're doing 0 minus v naught y. So we have negative 4.08 meters per second over negative 9.8 meters per second squared. And that would give you a time to the maximum height, which I'll call T max here, of 0.416 seconds. And now, of course, we've got to double that to find our total time, and I'm just going to have to squeeze this in here super small. The total time is 2 times T max. And as you can see here pretty clearly, if I do 2 times 0.416, then that's going to give me 0.832. But if you actually take the whole calculator answer and you multiply it by 2, you get 0.8326506. And so it basically gives you the same answer here, 0.832, 0.833, who cares? Same thing as far as we're concerned. And so that's your alternate solution for that one. And so now that we have the total time from whichever method you use, we can go ahead and add that to the chart here, 0.833 seconds. Of course, the time over here would be T max, which you could write as 0.416. And that, of course, really comes down to how you found it, too, just to be clear. Because if you found 0.833 and you divided it, you get 0.4165. And so technically you'd round it to 0.417. But I want to be very, 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 very clear about something. Please do not twist yourself up in knots about this, because nobody cares. The difference in 1,000th of a second is immaterial, because you're never going to be able to measure that with like an ordinary stopwatch. So I know a lot of you are thinking like, well, if you follow the rules for significant figures, don't we have to be very careful when we're doing an experiment? If you were doing an experiment with this thing, you wouldn't care, because your stopwatch is never going to measure with precision that much of a difference outside of the range of experimental error, because your reaction time is many, many times more than 1,000th of a second. And natural variation in your reaction time is more than 1,000th of a second. So it's really not that big of a deal. And so that was part B. Of course, part B really, though, was asking you for the 0.833, because the specific phrasing of that question was, how long did the ball take to return to the launching height? And then part C, the last part of this question says, what was its range? And it's very important for everybody to remember, I think, that the range is the word that we use for the horizontal distance. Of course, the vertical distance is what we call the height. And so we go ahead here and use our good old-fashioned displacement equation, literally the only equation that works in the horizontal direction, to find delta x, and that would be delta x equals v naught x times t plus 1/2 ax t squared. Of course, that acceleration term goes because there's no acceleration horizontally. And so we have delta x equals v naught x times t, and that gives you a 1.82 meters per second times 0.833 seconds for a grand total for a range of 1.51606, or to 3 significant figures, 1.52 meters. And that's it for that problem. Looking at the chart now, we've basically filled in everything. Of course, recognizing that this time to the maximum height is just half of that total time, we're done. That's all they could ask you. How could they make this more complicated? Really, is they could just make these numbers different. The ground won't be level. But again, it's actually not that crazy, because all you have to do is just put in whatever they tell you. If they tell you the ball starts a meter off the ground, you just put a meter in there. If they tell you it ends up on a cliff 2 meters above that, then you put 3 meters as the final position. And then you just work it. Unfortunately, some of them work out to be a quadratic. But since you already know how to solve that, it's no problem. So the main question we want to answer today is, how can you apply concepts of projectile motion to be able to answer like conceptual questions? We're going to do that shortly. But one question that we have to be very careful about answering, and we have not really addressed this yet, is the following question. What would happen to the range of the projectile if the angle was lower? I want you to take a second to pause this video here and think about that. What would happen to the range of the projectile if the angle was lower? Take like 1 minute to pause this video and think about what the answer is, and when you hit play, we'll go over it. Okay, so the question here that we asked was, what would happen to the range of the projectile if the angle was lower? And so it's important to realize here in this original situation, we had a projectile being fired from ground level at an angle of 66 degrees. And so that would look something like that. And so the question is, well, what would happen if we lowered the angle to something like, say, 15 degrees, or even something like 50 degrees? The answer is, it depends. Answering questions about what would happen to the range if the angle was lower is actually a pretty complicated question, because what you need to realize is that the range is like a very temperamental measurement. Because if we look at the equation for the range using the displacement equation, v naught x times t plus 1/2 at squared, it is always the case that this term is going to go away here, the 1/2 at squared term. And so what we get is delta x equals v naught x times t. And that equation for these projectile motion problems is always going to be true because the object isn't accelerating in the x direction. So obviously, looking at this equation, we see two key relationships. And that's that delta x is directly proportional to t, and delta x is directly proportional to v naught x. And that, of course, gives us a problem. Why does it give us a problem? Well, we have to do some analysis. So the first thing that we can say here is that the equation that we use in general to find v naught x is the equation v naught x equals v naught cosine theta. And so according to this equation here, we see that v naught x is directly proportional to cosine theta. And so now, of course, a perfectly reasonable question for us to ask, as we already have asked since we started this topic, is what is going to happen to the cosine of the angle as the size of the angle increases? And as we saw when we checked on the calculator, and you could do this right now if you forget, although I would imagine almost everybody knows this already, the cosine of the angle is maximized in the first quadrant at an angle of 0 degrees. And it's 0 at 90 degrees. So as you increase the angle, the cosine of the angle gets smaller. So just as a little shorthand notation here, I'm going to write as theta and then upward arrow. Obviously, that means increases. So as theta increases, the cosine of the angle decreases, which means v naught x is going to decrease because v naught x is directly proportional to cosine theta. And so just to finish this off here, we have to answer the pretty simple question here, which is, okay, well, if that's true, well, then what's going to happen to the range? Well, as we said over here, the range is directly proportional to v naught x. So we can say here, since v naught x decreases, delta x will decrease because delta x is directly proportional to v naught x. So looking just at what should happen to the range based on the angle increasing, we should see the range decrease. But of course, the question was asking what would happen if the angle was lower. And so everything that we have to say here is actually reversed. And so as the angle decreases, the cosine theta is going to increase. And then everything is going to be opposite of what we just said. And so I wanted to do this both ways so we can get a sense of going back and forth and trying to figure this out here. So the question is asking us as the angle gets lower. And so as the angle gets lower, the cosine of the angle gets higher. And because v naught x is directly proportional to cosine theta, that means v naught x is going to get higher. because V naught x is directly proportional to cosine theta. And since V naught x is going to be getting higher here, that means the range should be getting higher because delta x is directly proportional to V naught x. So looking at this just from the perspective of the V naught x, we would expect to see the range increase when the angle decreases because the V naught x would increase. And so I guess we'll just keep track of our results over here by saying as theta goes up, the V naught x is going to go up. But of course, the obvious question here is now what about the time? Well, the equation that we use for the time is that the time is equal to negative V naught over A. And if you forget, this is, first of all, an equation for the time to the maximum height. But that's fine because the time to the maximum height is just half the total time. So whatever happens to the time to the maximum height is also going to happen to the total time, right? Because if half of the total is the thing that now is smaller, the total is going to be smaller. So we can just use this for simplicity. And because the object stops at the maximum height, we can say here, at the maximum height, the VF is equal to 0. And so when you take 0 equals V naught plus AT, there's a T over there that got cut off, then solving this for T would require us to subtract V naught and then divide by A. Okay, so now we've got to make this a little more complicated. V naught, remember, is the V naught in this equation, remember, the V naught in this equation is actually V naught y. And the acceleration here is the vertical acceleration, which is the acceleration due to gravity. So what I'm going to do here is I'm going to write V naught sine theta for V naught y, and I'm going to just write over g here. And the reason why I can get away with that is because A is equal to negative g. And that's only because if you look in your AP Physics reference table, you'll see that the value for the acceleration due to gravity on the Earth's surface, g, is just a positive constant. And so we don't need to go too nuts about the sign here. But the point that I'm trying to make is we can just simplify this by getting rid of the sign if we just say that A is equal to negative g, because g is a positive constant. And so according to this equation, what we end up seeing here is that the time is directly proportional to sine theta. Now, I don't want to do what I did over here because I fear that may have ended up confusing some of you. The angle here is going down. As we saw the other day, the sine of an angle is maximum at 90 and minimum at 0 degrees. So the sine of an angle is 1 at 90 degrees and 0 at 0 degrees. So as the angle increases, the sine actually decreases. Of course, because the question is asking us something opposite, here the angle is decreasing, we have to be careful about that. So what we've established so far here is that the time is directly proportional to the sine of the angle. And so what we can say is as theta decreases, the sine of the angle decreases, which means basically that the V naught y will decrease because V naught y is directly proportional to the time. And so since the time is directly proportional to V naught y, that means the time, technically, as you can see here, is directly proportional to the sine of the angle, which means as theta goes down, the time is going to go down. And so decreasing the angle makes our time go down. So now we see a strange result here. Because when we decrease the angle, we make the v naught x bigger, but we make the time smaller. And so the obvious question here is, by how much does it cancel it out? Do these two effects cancel each other out? Do they not? How can we tell? We have to see. And I think the most straightforward way for us to go about doing this is to play with these values in Excel. Because there are two ways that you can understand this, I think. And the first way is I can just tell you and you can force yourself to memorize it. And like, that's kind of lame. The second way is for us to really observe what's happening here and see if we can figure it out ourselves. And so what I've done is I created a little spreadsheet so far, and I just made up some numbers. And so here, what I have for my initial velocity, which of course is measured in units of meters per second, I'm going to call that 5. And I've just got a range of angles here from 0 degrees to 90 degrees. And of course, because these are degrees, and I don't want this to get confused, as you'll see in a second, I'm going to label this as being in degrees because that's going to be very important. And I'll just move that out like this. Now, I would hope that everybody knows so far that the sine of 30 degrees is a half, right? But notice in Excel, if you use the sine function and then you go to the angle 30, it does not give you a half. What should you be thinking when you're seeing that for sine of 30? I hope you guessed it. Excel uses angles in radians because they're annoying. But what they do have, which is pretty sweet, is a radian function, which converts degrees to radians. All I have to do is that, drag it down, and now I have all my angles in radians. Notice what the main thing we can check to make sure we've done this right is check out 90, because notice 90 is 1.57. And since pi is 3.14, 1.57 is half a pi. And if you remember, pi radians or 3.14 radians is 180 degrees. So pi by 2 radians or half pi radians is 90 degrees. Okay. So let's work some magic here. As we saw, the time is equal to v naught times sine theta over g. And we can formularize this. That's not a word, but let's just pretend it is. We can formularize it. Sure, let's lean into it. In Excel, and start to get some good numbers here. So we have to take v naught times the sine of the angle over g. And you know what? I'm just going to throw g up here as well, so I can just click on it instead of having to type it in. So we have the time is equal to v naught. I'm going to use double parentheses here for my numerator. I've got v naught times the sine of the angle. That's my whole numerator right there. And then I'm going to divide that by g, and I get a number. And of course that's 0, because when you shoot the thing at 0 degrees, it doesn't go in the air at all. It just immediately hits the ground. But of course, when I drag this down, we should see some good looking numbers, but we don't. And it's probably because it went to B2 and then B3. Yeah. So I'll just have to change all these to B1. Keep that in mind when you're using Excel. Sometimes Excel is just dumb. It should be going to D5, and then that's over E1. Okay, and so now if I grab these two and I fill it down, it learns. It doesn't learn. Okay, I'm going to skip ahead here and cut as I fill these in, just so you don't have to sit here and watch this. Okay, And so the way to properly do that, the way to properly do that, so the way to properly do that is probably just to type in the number instead of clicking on the cell, but I suppose we'll be able to see that here in a minute. And so now we have a table with all our time values. And I don't really care so much about this, but let's just go to 3 sig figs and call it a day. Okay. So now for our range, if you remember, our range equation was equal to V naught x times t. So now that I have my times, I'm all set. I just got to do V naught x times t. So I'm going to do equals. And I've got my 5 meters per second times cosine of the angle. And that's my whole numerator, or at least the first part. And then I got to multiply that by the time, which here is going to be B4. And that's it. I've got no range there. And I'm filling in values as we go along. And so I'm going to fix this to be 3 decimal places also. Huh. You see a weird little result. And so I'm going to go ahead and I'm going to copy this over here. And I'm going to paste the values only. Remember, you got to do that. I'm going to fix these to 3 sig figs again. 3 decimal places at least. And I'm going to paste this, copy and paste it over here, because I want to see what's happening. And the way that you can see what's happening here, it's important to realize, is by plotting, right, the range versus the angle. And actually, because degrees are more familiar with us, let's go ahead and just plot this versus the degrees. That'll make life easy. Okay, so let's plot this thing and see what's what. So we'll do a little scatter. Ooh. And we could do a line of best fit. And let's make that a polynomial. Ah. And now we see what we need to see. So notice here, it doesn't really help. We see this nice sort of parabolic function. And what should definitely be noticed is something you may remember from honors physics. The range is a maximum at 45 degrees. The range is a minimum at 0 degrees and 90 degrees. But what's also nice about this graph is, I guess I can't put a line in there, but what you should notice is that these points, notice the ones that we had closest to 45 were 30 and 60. Was 30 degrees, notice the first coordinate, and then 60 degrees are the same amount away from 45. And what you see is that when the angle, because of the symmetry of this curve, when the angle is the same amount away from 45, like 75 and 15, we see the exact same range. So because the question that we originally asked here, which was what happens to the range if we decrease the angle, is actually too vague to be answered, we can at least go ahead and try to explain why 45 degrees produces the maximum range. And so that's what we're going to do here, because that's actually a very important fact. So the first thing we can say here is that the range is based on V naught x and the total time, as we just saw. And so since V naught x is equal to V naught cosine theta, V naught x has a maximum value at 0. And of course, that's because the cosine has a maximum value at 0 degrees. Also, since the time is equal to V final minus V initial over AY, we can actually just write this equation for the total time, And so remember, VFY, when this thing reaches back to the ground level, is just the negative of the initial velocity. So we can write negative V naught y minus V naught y over AY. And now, of course, because we have negative V naught y minus V naught y over AY, we can write that as negative 2 V naught y over AY. So since t equals negative 2 V naught y over AY, and V naught y is equal to V naught sine theta, the time is largest when V naught y is largest, which is at an angle of 90 degrees. So they conflict, as we mentioned. But 45 degrees produces the maximum range because 45 degrees is the angle at which the product of V naught x and t is largest. And so since V naught x and t are maximized at opposite angles, V naught x is maximized at 0, t is maximized at 90, 45 degrees provides the perfect balance between the two. For angles larger than 45 degrees, the time will be large, but the V naught x is going to be too small. And so the product of V naught x and t is not going to be big enough to give you that maximum range. For angles smaller than 45 degrees, the V naught x will be large, but the time will be too small. And so the product of the two of them is not going to be big enough to give you the maximum range. At 45 degrees, we see the biggest product of V naught x and t, basically because the product of V naught x and t, if you actually write the whole thing out, and I'll do this up here real quick, the product of V naught x and t, as you can probably tell, essentially comes down to the product of the cosine theta and sine theta. And because cosine of 45 is 0.707, and the sine of 45 degrees is also 0.707, because 45 degrees is the angle where the cosine and the sine are the same, then 45 degrees is what gives you the biggest product of cosine theta and sine theta. And so 45 degrees gives you that maximum product of cosine theta and sine theta. And so we can say that's the biggest product of V naught x and t, which gives us our maximum range. This is actually a very important point, not just to know, but to be able to understand and explain. So I'd like you to go ahead and pause this video here and write that down. And when you hit play, we'll move on. So last thing I want to do while we're on this point is just to address one last thing. And that was about the symmetry in the curve for the range versus angle graph. The fact that that graph was symmetrical tells us that we see this sort of quirky range dependence on the launch angle. Now, this particular diagram just happens to be for a launch velocity of 50 meters per second. We see that clearly 45 degrees, which is this line right here, gives us the farthest range. But when the angles are complementary here, meaning they add to 90, like 75 and 15, they give you the same range. Also for 60 and 30, they give you the same range. And that's an interesting little result. I'd like you to go ahead and take a second to pause this video here and copy down this chart. Now, I do not want you to number or label whatever we're saying here, the axes. I just want you to make a rough sketch of the trajectories. So really even just something like this. You make one line and just make it big and actually curved, and you'll call that 45, and then you'll show a 75, and then a 15, and you'll label them, and then you move on. 30, 60, whatever, you move on. The one thing I want to mention before you do that, though, is notice this fits with everything that we just said on the last slide. 75 degrees, because the angle is huge, it has a really large V naught y, so the max height is high and the time is really large. But it doesn't have enough horizontal velocity to be able to make it. Conversely, 15 degrees, it has a super large v naught x, but because the v naught y is so small, it doesn't get much hang time because it doesn't get too high in the air. And so gravity kind of just pulls the thing back down to the ground really quickly. The same argument, of course, could be made for 60 and 30. The lower angles have a larger v naught x, but a smaller time, whereas the larger angles have a larger time, but a smaller v naught x. Take a second to pause this video here and sketch that diagram. And when you're done, we'll write one quick note, and then we'll move on to some conceptual problems. Okay, so our one quick note before we move on here, this is an important point. When two angles are equidistant, or in other words, the same amount away from 45 degrees, they will produce the same range if the launch velocity is the same. So for any two angles that are the same amount of degrees, the same number of degrees away from 45, they'll produce the same range with the same launch velocity. Of course, that's kind of a wordy explanation. You're all smart. If you just remember it as complementary angles will give you the same range, then you're in business. The key detail, though, is remembering that that's only true when the launch velocity is the same. Take a minute, pause this video here and write that down because that point is very important. And when we hit play, we'll go ahead and answer some conceptual questions. Okay, so if you go back to the post on Google Classroom, you will see an attachment to that post, which is a worksheet, which is entitled Vertical Projectile Motion Conceptual Understanding Number 1. And there are two questions on the sheet. One of them is on the front and one of them is on the back. And I'd actually like you to start with the one on the back. So this question, B2QRT09, is giving you a projectile fired at an angle. And they're asking you on the axes to sketch graphs for the horizontal velocity and the vertical velocity versus time, and then the horizontal acceleration and the vertical acceleration versus time graphs. I'd like you to pause this video here and take a few minutes to complete this, and when you hit play, we'll go over it. Okay, so it says on the axes below, they want us to sketch graphs for the horizontal velocity and the vertical velocity versus time. Pretty easy. We should know by now that when an object is projected at an angle like this, it has no horizontal acceleration. And so that means we should see a graph with a constant zero slope for the horizontal velocity versus time. And that means the graph should look like this, with a nice straight line with no slope. Now, I'm sure some of you are thinking, wait a second, why did you put the line there? If you look at the instructions, and I'm just going to try to draw that straighter before we move on here. Not really. Okay. If you look at the instructions, you'll see here that this question says, take the right as the positive horizontal direction, and these little motion lines are showing you that the ball is going to the left here. You gotta make sure when you're looking at these questions that you read the directions. It would be devastating if on the AP test you had a question as easy as sketching graphs of horizontal velocity for a projectile fired at an angle and reading the directions caused you to get the problem wrong. And so here we should expect to see a graph with no slope. And then for the vertical velocity, let's just check here. Of course, now it says up is going to be the positive vertical direction. And so we will say in the beginning here, this object has a positive initial velocity. Then in the middle, it has 0 velocity. And on the way down, it's going to have a velocity which is negative and increasing in the negative direction. And so we should see a graph that looks something like this. A straight line with a constant negative slope. And we'll do both explain your reasonings at the end. So your velocity versus time graphs should look like this. For the acceleration versus time graphs, well, these are easy. As we already mentioned, in the horizontal direction, the object doesn't accelerate because there are no horizontal forces to cause horizontal accelerations. So we just see a line with zero slope like that. And for the vertical acceleration, we just see a constant negative acceleration, of course, an acceleration of negative 9.8 meters per second squared. And so to explain our reasoning here, well, there's not a whole lot we should say. We'll say first, the horizontal velocity versus time graph should show a constant velocity because the horizontal acceleration is zero, as there are no horizontal forces. Since the slope is the acceleration, the slope of the graph should be zero. And basically for the vertical velocity versus time graph, we'll say the same thing. The vertical velocity versus time graph should show a constant negative acceleration because the force of gravity causes the object to accelerate toward the Earth. Since the slope is the acceleration, the slope of the graph should be constant and negative. And then for the acceleration graphs, we could just say something like ax equals 0 meters per second squared. There are no forces. You don't need to go nuts about those because they're so simple. And then the vertical acceleration, that's it. Take a second to pause this video here and write that down. And when you hit play, we'll do that question on the front of the sheet, and that'll be it for today. Okay, so on the front of this sheet, there's another nice graph question. And these are very similar, but I want you to just take a second to go through these. Basically, they're giving you a very similar situation and asking you to pick the shapes of the graphs. So just go ahead and take that for a moment. And when you hit play, we'll wrap this one up. Okay, so the key detail here in this problem, and really the whole purpose of this, well, there were two purposes to this sheet. Is one, make sure everybody remembers that the graphs here for a projectile fired at an angle are the same as the graphs for an object thrown straight up in the air in the horizontal direction, in the vertical direction, and in the horizontal direction, it's just a constant velocity problem. And also direction reading. That's very important. So it says here, use a coordinate system with up as the positive vertical direction and to the left as the positive horizontal direction. So now the positive horizontal direction is to the left, and that's the way the ball is going. So the horizontal velocity versus time graph should show a positive velocity, which is constant, and that makes the answer here A. The horizontal acceleration versus time graph is going to be C. The vertical velocity versus time graph is going to be I. And the vertical acceleration versus time graph is going to be B. So horizontal velocity A, horizontal acceleration C, vertical velocity I, and vertical acceleration B. And of course, the explain your reasoning is the same as what we just wrote for the last one. So we could just leave it at that. It's very important for everybody to notice the trends here. Because what we're going to look at tomorrow in terms of conceptual problems is we're going to see the difficulty, I think, step up compared to these kind of graphing questions. But it's very important for everybody to remember a projectile fired at an angle is basically just two problems in one. A constant velocity problem in the horizontal direction and an object thrown straight up in the air in the vertical direction. And that's why for the vertical direction, we see that the vertical velocity versus time graph looks exactly like the velocity versus time graph for an object thrown straight up in the air. And of course, the vertical acceleration graph looks the same as the acceleration graph for an object thrown straight up in the air. Making those connections here is going to be very important and will sort of help you as you try to sort your way through the math as we go forward. All right, everybody, that's it for today. Have a good one.